Good morning, afternoon, wherever you happen to be. My name's Mike Panaki, owner of Network Protocol Specialists LLC here in Seattle, Washington. And today we are going to be talking about Wireshark. I've been doing these sessions. I want to talk about a variety of different technologies. I work with everything from the physical layer all the way up to the application layer, troubleshooting problems. And I want to introduce you to some technologies, clear up some myths, things like that. So whether you're joining me on Facebook, LinkedIn, or YouTube, I've got the comment section up here. So if you have any questions as we're going along, please feel free to throw them in the comment section, and I will do my best to get an answer to all of those, or as many as I can. So what we're going to do is we are going to go through some of the tips and tricks in capturing with Wireshark. Maybe you've been using it for a while. Maybe you just started or you are curious about it. So I'd like to go through a few things that I've learned over the decades that I've been capturing packets. Just to date myself, I started capturing packets back in probably about 1993 on a Banyan Vines network, using a network general sniffer. So things have changed a lot since then. And fortunately, there's free programs out there like Wireshark that allow us to get in there and see what's going on. Now, is packet analysis the solution for everything? No. There's a time where I probably felt like it was. But honestly, there are times where there's other tools out there, SNMP, ping, trace route, that are going to help get us close to what's going on. But what I found is on those really difficult problems, especially those problems that deal with application performance problem issues, doing packet capture and analysis is a great way to go. So what we're going to do is we've got a few different topics we're going to talk about. And the first topic that we are going to talk about in here is getting in the path of the packets. Because honestly, until we get in the path of the packets and we can capture the correct packets, it doesn't mean anything as far as the trace that we're looking at. I have gotten sent traces over the years where people have done a capture about the time the problem happened, and it turned out that they just didn't have the right packets. So we're going to talk about a few different ways that we can get in the path of the packets. Now, one of the easiest ways is just to install Wireshark on the machine that's having the problem and do the capture there. We're going to get to that in just a little bit. But sometimes we need to capture the packets as they're going across the network. Now, what do we know about an Ethernet switch? Well, an Ethernet switch has a bridge forwarding table in it that directs packets to the proper destination. So that means that if I plug my laptop into a switch port and there's a conversation going on between two other switch ports, I'm not going to see it. I need to inject myself into the path of those packets. So we're going to come over here. We're going to take a look at a few different ways that we can get in the path of those packets. So we're going to start out by switching over here. Let me clear a couple things off here before I switch over there. So let's switch over here. And here is about the simplest setup that I've got. And that is that right here, we have our Netgear GS105E switch. Now I've got a nice little video out on YouTube that talks about this switch and how to turn on port mirroring on it. So what I've done with these is I wanted to find out the cheapest switch that would support port mirroring and set that up so I could use this to get in the path of the packets. So in this case, what I've done is I've taken this Netgear GS105E, and if you search YouTube for Netgear GS105E, you're going to find that video. It's going to show up as one of the top ones. And I'll even put in the comment here. Tell you what, I'm going to put in the comment right there. There is, we'll send that out. That is the link to the YouTube video on how to turn this into a tap, into a device we can use to help us capture packets. So what I've done is I've set this up so it's mirroring the traffic from port 1 over here to port 4. So I've got my laptop. The laptop that I'm using to do this broadcast plugged into port 1. I've got my analyzer plugged into port 4. Port 5 is connected to the rest of my network. So now I've put myself in the path of those packets. So this allows me to come in here and start capturing all the packets that are going between these two ports right there. So for about $35, I can go in and I can set up a little device like that to get in the path of the packets. Now, what's the downside of a device like this? If I came in here and I pulled this power cord right there, we would lose this stream. Why? Because this will not forward packets if we kill the power to it. So that's where we need to ask ourselves when we're going in and doing packet capture, am I willing to put something like this in the middle of my network? And if I lose power, I'm going to take down that network. So this is where we start getting into some other devices for capturing packets. Now, if you have a managed switch, you can certainly go in and set up a mirror port on that managed switch. You can tell the switch to take the traffic going in and out of one port and copy it over to another port. That's a really easy way to go do that. There's some downsides to that. You can lose packets, especially if you try and span too much traffic. Your timing can get thrown off. So let me just show you a few other devices that we have back here. And the first one is an inline fault-tolerant tap. So in this case, with this inline, we'll push that out of the way right now. With our inline fault-tolerant tap, what this does is we can put this in line with the network and we can connect it to our analyzer. This allows us to go in, capture the packet or get the packets and forward them over. And if we kill the power to this, this will recover in about 26 nanoseconds. So this provides a means for us to get in the path of the packets without damaging or causing problems on the network. Now, another option is something like this. This is a fiber tap. So this does an optical split on the light. So we pass the network through these two ports, and the traffic going in and out of ports A and B are sent out these two fiber ports right there. So this is another way that we can go in and monitor traffic out there using a tap. So getting in the path of the packets becomes critical. Now I'm going to flip over here, and here is where we really step things up. So this is a product called the Booster from ProfiTap. And what this does is I have this tapped into 4 1 gig connections, including my internet connection. It aggregates all that traffic into a single 10 gig connection and sends it up over here to this IOTA. Now, the IOTA is the device I'm using to do the captures. So what we can do is we can go in and use that to tap into a number of connections and capture that as well. Now, somebody brought up a question. Can we capture Wi-Fi traffic? Wi-Fi is tricky because with Wi-Fi, we have to be able to get down into the drivers and be able to capture the packets. So I have found the greatest success in doing Wi-Fi traffic capture is by using a device that's specifically designed for that. We can also use wireless access points in many cases. So probably the cheapest and easiest way to do a wireless packet capture is to look to see if the access point you're using supports wireless capture. So I was doing some troubleshooting on a Meraki network. We were able to use the Merakis to do the capture. We can use, I use a lot of MikroTik routers. I can use those for doing capture. Over my shoulders, we've got some equipment from NetAlly, and one of those is the AirCheck G2. Now, the AirCheck G2 is designed to do 802.11 AC and below wireless packet capture. Now, somebody else brought up monitor the port of the AP. Great response. And why I like that response is because when we get into capturing wireless traffic, we have to decode that traffic. So there's times where we want to be able to see the contents of the packets. And if you're using something like WPA2 personal, we can put in the pre-shared key and we can decode that traffic if we capture the beginning of the conversation. We have to capture that four-way handshake between the client and the AP. If you're using something like WPA2 Enterprise, we're not going to be able to decrypt that traffic. So if we just want to look at the Wi-Fi communications, we can capture on the wired side. But I'll tell you, honestly, it's easiest to capture on the access point, the wired side of the access point, and see the traffic there. All right, so we're going to be talking about Wireshark. So let's dig into Wireshark and let's take a look at a few things on there. So what we're going to do next is we're going to take a look at a Wireshark overview. So you can go out to Wireshark and download it. Now, what I'm going to do is I'm going to come in here and share my screen. Now, I'm running Wireshark on a MacBook. Now, when we're running it on a Mac, we have to run Wireshark as root so that we can see the interfaces on it. If you're running it on Windows, you're not going to have the same problem. So in this case, what I'm going to do is I will come in here and we'll just grab this window right here. And I'm going to go ahead and I'm going to start Wireshark as root. I'll type in my password, and that's going to fire up Wireshark. So here we go. So let's go ahead. You don't necessarily need to see me for this part. So let's go ahead and have that take up the whole screen right there. So when we first log into Wireshark, here's what we see right here. We see our various interfaces that we have available to us. So in this case, I've got my USB 10100-1000 interface. That is the one I'm most interested in. Now, if I don't capture using root, I won't see that interface. So let's just go ahead and start capturing some packets. So I'm going to double click on that interface, and here we go. We see that we've got packets going across. So I'm going to stop this. Now, one of the things that oftentimes happens when we first start with Wireshark is we get a lot of information and we may or may not know what we're looking at. So let's talk about a couple of things that we can do to make Wireshark easier to use. The first one is not trying to remember every single IP address there is out there. So if I'm out here and I'm trying to remember, this device goes with this IP address and this device goes with that IP address, that can be troublesome. So let's do this. We're going to come over here and I'm going to go up to View. And I'm going to go into Name Resolution. Now, by default, Wireshark turns off network layer name resolution. Why does it do that? Because to do this, it's got to send DNS pointer record queries. And if we're capturing a lot of packets with a lot of IP addresses, this can create a lot of traffic at the time we're doing our packet capture. So by default, this is turned off. So one of the first things I like to do is I like to come in and turn that on. So I'm going to turn on Resolve Network Addresses. Now what's going to happen, and we can say, we're going to see that it is going to start putting in some names to go with those IP addresses. So in this case, I can start seeing some DNS names that go in here. Now, there has to be a pointer record out there for that device for it to be able to resolve that name. The next thing I can do is over here where I see 10.0.0.11.122. That's my PC. So do I always want to remember that's my PC? No. So what I can do is I can right click and I can say Edit Resolved Name. Now up here at the top of the screen and my logo, let's get rid of that for right now. We'll turn off that logo for a moment so it doesn't hide anything over there. But what I can do is right up here at the top, it says address 10.0.11.122. I can give it a name, Mike MacBook. I'll hit OK. So now it puts Mike MacBook in there. So anytime I'm looking at my trace now, it's going to show that 10.0.11.122 is my MacBook. That makes it easier to follow along and see what's happening in the trace. Now, the other one that I change right off the bat, and in fact, let's do this. Let's see if we can, I don't want to do it on that screen. I want this screen. I'm going to make the font a little bit bigger here so that you can see it. I want to make sure you can see everything okay. Let's change our column widths. But over here, what we've got is in our time column. By default, with my time column, it is showing the time since the beginning of the trace. So honestly, I could care less about the time from the beginning of the trace. Anytime I'm in there troubleshooting problems, I care about the time between packets because nobody has ever called and said that an application is running too fast. They always call and say the application is running too slow. So what do? Well, we come in and we change our time. So I'm going to come up here, I go to View, and I'm going to go to Time Display Format, and I'm going to go to Seconds since previous displayed packet. So now it's showing me the gap between each of the packets. So I can use this gap to start getting an idea of what's going on the network. So now we've come in and we've started setting up the display. We're getting the display so that it is working for us, so we can see exactly what it is that we're looking for. Now, the next piece in here is I want to come in and start setting up some capture filters. Now, I know you want to capture everything. You want to capture it all, and it's really not a bad idea because if you don't capture everything, there may be some things you miss. But sometimes maybe there's a bunch of traffic going on in the background and we don't care about that traffic, or we're concerned about a particular port. So in that case, we can set up a capture filter. So if I come up here and I go to capture and I go to options, I can come down to my capture filter for selected interfaces. So I've selected my USB interface I'm going to use for doing my capture, and I could go in and type in host, and notice how it gives me some suggestions. It tells me if you're going to type in host, here's some things you could type in for that. So, or I could type in port. So let's say I'm interested in port 53. I'm interested in my DNS traffic. So now, if I hit start, it's going to say, whoa, you haven't saved that trace you had before. Are you sure you want to throw that away? Yeah. So now it's going to go in and start looking at my DNS traffic. So what I'm going to do is I'm going to come back here. We'll go out to Amazon. Let's go out to a few websites here. Let's see. A lot of these are probably cached on my machine. Let's try YouTube. So what this will do is this is going to go out and start capturing that traffic to and from my machine and these various hosts out here. So I can start getting an idea of what my DNS queries look like. So DNS, one of those protocols that's key to being able to go in and communicate out there on the internet. Well, I can come in and I can see right here, I send this query out for DNS or for Google right there. And I get a response back right here in frame number 2. Now, remember, we set that time field to look at the time between the frames. So I sent my query out here. I got a reply back in 65 milliseconds. Wow, that's pretty good. Now we see this 911 milliseconds. Should I worry about that? Not really, because that is the time between this response and when I sent my next DNS query. Now that DNS query, we got a response back in 1714 microseconds. So we can start getting an idea of how long it takes to send packets back and forth. Now, what I'm going to do is I'm going to come up here and I'm going to open a trace file. First, we're going to stop capturing. And we're going to open up the old .cam trace file. Now, this trace file I captured 18 years ago. 18? No. Let's take a look. If we come into this frame right here, and we look at, yes, it was captured in 2003. So even a trace that is old enough to vote is still good for demonstrating things. Now, in this case, we see a variety of things. We see some TCP SYN packets. We see some ACKs. So this is where we capture traffic going between my machine and the Washington State Department of Transportation. And some of the communication was slow. The website was slow to load up. So let me show you a few handy things here. When it comes to filters, I can come in. I'm going to grab frame number 24 right here. One of the handiest filters in Wireshark is to come in and right-click and go to Follow TCP Stream. So what this does is this sets up a filter for just the communication between these IP addresses and using these ports. So now I'm looking at this specific stream. So I can see right here, I do my TCP three-way handshake. Now remember, when we're going in and doing troubleshooting, we are doing protocol analysis. So with protocol analysis, we are looking at, are these devices acting like they should? So here I send my TCP SYN. I get a SYN acknowledgement back in 39.8 milliseconds. That is the round trip time between my device and the server. So I don't have to try and do a ping. And really, that was the round trip time 18 years ago when I did this capture. So that gives me an idea of what does that round trip time look like. Now, when I come in here, I can see that I then send an ACK. That's the third part of my three-way handshake. So I've completed my three-way handshake. That is great. Okay. Now, I can come in and I can see that I sent a HTTP GET. Now, this was back in the good old days before HTTPS, and we could actually see what was going on in our packets. But here we send our HTTP GET. Now, our HTTP GET, it takes us 130 milliseconds to get a response from the server. Now, this starts giving us an idea of, is it a problem with the server or is it a problem with the network? Because if I know it takes 39 milliseconds to get a reply back from that server when I sent my SYN, it takes 39 there, it takes 130 there, that is probably 39 plus the delay on the server to create that interface right there. Okay. Now, in this case, it said use local copy. So it told me, you have that cached on your machine. You don't need anything from me. So now we close up our connection and we're done. So that is what we see with a pretty typical connection. Now up here we see TCP stream equal. So that is our stream index. So for every TCP conversation within Wireshark, we have an index. I could change that to 11 and apply that filter, and boom, there's the next conversation, right? I could do 12. There's the next conversation. So what we're doing is we're filtering down on that TCP stream. Now, Nick brought up, is that the same as the index column? Sure. I could come in And we're going to see that there's our stream index right there. And when we start looking at that, I could right click on that field and I could say apply as filter, selected, and it's going to do the same thing. So I could grab any packet within a TCP stream and take a look at it. But now let's go ahead and let's jump in. And what we want is we want to find the bad packets, right? We don't care about the good packets. We want to find the bad packets. So here's what I'm going to show you. And this is how we can start modifying Wireshark to meet our needs. So we're going to apply a display filter here. So let's go in and we're going to apply that display filter. And in this case, we want every bad TCP frame. So there's a nifty filter for that. And that is tcp.analysis.flags. So you notice, and I know that the screen's a little bit small up there, but you notice that down here, up here in the corner, when I typed that in, it started showing me suggestions. And if I get the filter right, the display bar turns green. So now I'm going to go ahead and apply that. So now, look at all these retransmissions. So now we start seeing TCP retransmissions. So what's a retransmission? Well, a retransmission is any case where I send a TCP frame and I don't get an acknowledgement for it, and I need to resend that TCP frame. Every time I send a TCP frame, I start a retransmission timer. When that timer expires, if I haven't gotten an acknowledgement yet, I resend the frame. So let's go in and let's take a look at one of these. So I'm going to grab one in here. How about a SYN? I'm going to grab a SYN frame. And I want to grab one right there. Let's grab this one right here. So I'm going to right click and I'm going to follow the TCP stream. Let's see what happened with this TCP stream. So in this case, what happened was I sent my TCP SYN right there. And I waited 2.9999 seconds. I haven't gotten my SYN acknowledgement back. So I resent the SYN. Now, if we were to go in, and especially with Windows at the time this capture was taken, the initial retransmission timer for TCP was 3 seconds. So our machine patiently waited 3 seconds and retransmitted the frame. Then we see that within 41 milliseconds, we get a reply back. And that is in line with what we saw before. It was about 39 milliseconds before. So that's in line with it. But this TCP SYN packet was lost somewhere along the path. So we waited 3 seconds, and this is just adds insult to injury. Right here, we say, get this header image. It says, use local copy. You already have it. So here's an example of where I already had it cached on my machine. And I said, hey, I want that. And we waited and waited and waited and waited a long time. When it comes to networking, 3 seconds, very long time, only to find out we had the correct image cached already on our machine. So what I'm going to show you next is, I think, one of the coolest things in Wireshark. And that is we can now start creating profiles. So profiles are a way that we can customize Wireshark for a specific protocol. So I'm going to come up, I'm going to go to Edit, and I'm going to go to Configuration Profiles. And we're going to drag that window back over here. So it shows these different profiles that I've already created. So we're going to create a new profile. We're going to call this webcast. I'll hit OK. So now what it's done is it's taken my default profile and copied all the settings over to webcast. And we're going to make our font bigger again so that you can see what's going on. Now, what I'm going to do, I got to be careful sorting on different columns. Sometimes there's some reasons that we want to do that. For here, not today. So in this case, we're going to go back, and the last 10 filters that I use are saved in this dropdown. So we're going to reapply our TCP analysis flags. And I'm going to come over here to the far right-hand side. And there's a little plus right there. I'm going to click on that. This is where I can save display filters I use on a regular basis. So now I could say bad TCP. Display TCP frames that are errored. We'll say that. And here we see our filters TCP analysis flags, and I'll hit OK. So now we've got a brand new button up there called bad TCP. So I'm going to close that. So when I come in and take a look at a trace file, I can come up here and I can say, hey, show me all the bad TCP frames. And I see all these retransmissions. Okay, so now I can start seeing all of these packets that are being retransmitted. Well, that's not good. Now, if I suspected that my network was a problem, I'm going to see retransmissions. I'm going to see packet loss, and that packet loss is going to cause slowdowns. But if I go in and I take a look at a trace and I don't see any slowdowns, if I don't see any bad packets, any packet loss, that can be an indicator that my network and packet loss on that network isn't what's causing the problem. So I use the bad TCP filter, the tcp.analysis.flags, as a way to quickly go in and take a look. How does this trace look? Are we seeing packet loss in there? If I am, then I'm going to move down the protocol stack and start taking a look at what's happening along my network. If I don't see packet loss occurring, I'm going to start moving up. I want to take a look at how long it takes to get a response from a device. Now, we're going to open a trace file here. Let's see if it's in recents. This is another one of my favorites right here. Now, with this one, probably too short. Let's open up a larger version of that. There we go. All right, so we're going to start out, we're going to apply bad TCP. Now we see a duplicate ACK and we see a retransmission, but we really don't see a lot of problems as far as TCP goes in here. So I'm going to go ahead and clear that filter. And you're not seeing my screen. That's all right. Now you do. So in this case, what I'm going to do is I'm going to come in here. I'm going to hit bad TCP. We see this spurious retransmission. This can be caused at the beginning of the trace by seeing packets that we really didn't see the initial packet, etc. Here we see a duplicate ACK, and we can get into that later if we have time. But for the most part, I'm not seeing a lot of retransmissions. So what I'm going to do is unload that filter. So this is another trace captured quite some time ago. I was going out to the Hilton website. So what I'm interested in is, where do I see the server taking a long time to reply? So what I can do is I can come into TCP and right-click, and I can go into Protocol Preferences. And what I want to make sure that I'm looking at is that I am calculating conversation timestamps. Now, when I calculate conversation timestamps, what that's doing is it's looking at the time between each packet within a TCP stream. So now, if we come in and we start taking a look at our TCP information, we see that right here it says time since previous frame in this TCP stream. And if I click on that, down here at the bottom, and I know it's really hard to see on this screen, but it says TCP.time delta. This is the time between TCP frames. So if I come up here and I say TCP.time delta, and let's say greater than 1 second, okay? So now, in this case, we can start seeing where we have TCP frames that took more than 1 second to get a reply. So I'll look at this one right here, frame number 11. I'm going to follow TCP stream. And let's see what we have going on in here. So in this case, let's make sure our time is set to seconds since previously displayed frame. So let's look at what's going on in here. So what's happened is we've done our three-way handshake. SYN, SYNAC. This tells me my round-trip delay for this connection is about 134 milliseconds. Then I send my ACK. Then I send my HTTP GET. Now, 125 milliseconds later, which is in line with what our round-trip delay to the server is, we get this acknowledgement coming back right here. How do I know it's an acknowledgement? Well, one, it says ACK, and two, the length is set to 0. Now, that length is going to be the length of the data that's getting sent back. So think of if you sent a certified letter. You send that certified letter out. When the person receives the certified letter at the other end, they sign a receipt, and that receipt gets sent back to you. So you get a receipt saying they received the letter. Now, it could take them 2 weeks to reply to that letter. And that is what we're seeing here, is that this acknowledgement that we get right here in frame number 10 tells us that our request, our HTTP GET, was successfully received by the server. Now, how do we know that it's that packet? Well, if we come in and look at frame number 9, right here, if we look at our TCP sequence numbers, we can see that our sequence number right here is number 1 for frame number 9. We see that our next sequence number is 349. That's because we sent 348 bytes of data. So our next sequence number equals our current sequence number plus the number of bytes of data we're sending, which also equals the acknowledgement number. So if we see an acknowledgement number of 349, that tells us it got sequence number 1 and all 348 bytes of data. So what do we see right here? Acknowledgement number 349. This acknowledgement right here goes with that frame right there. Now, how can I make that easier to see? One thing I'll do is I'll right-click on next sequence number and say apply as column. So right here it tells me what my next sequence number is. And I know that my next sequence number is also the acknowledgement number for that frame. So I can see right there, 349, ACK 349, this is ACKing that. So what that does is that tells me the server received the packet. But now it waits. How long does it wait? The server waits 4.85 seconds to send me a reply. So is this a problem with the network, or is this a problem with the server? In this case, this is absolutely a problem with the server. This is a slow server. The network got it there and sent me the receipt back in the amount of time I would expect. But the server is taking a long time to reply. So when it comes to going through these traces, these are the types of things that we're looking for. We're looking for packets that are lost. We're looking for TCP errors. We're looking for cases like this, where we see a delay out there, where we see that the packets are slow coming back. And how do we do that? We can use things like TCP time delta. So now I could add a filter for that. I could come back here. I could drop my filters down. I could see TCP time delta greater than 1. And let's apply that. Now we see some resets. We see some fins. So maybe I'm not concerned about fins. I'm not concerned about it taking a long time for it to close the TCP connection or for it to reset the TCP connection. So I could say and dot. We could say TCP dot flags dot reset equal 1, or TCP dot flags dot fin equal 1. There we go. Now that narrowed it down. Now I'm looking at data frames that are taking longer than 1 second. Now I could even adjust this. I could say half a second. Yeah, so we could say, what if it takes the server longer than half a second to reply? Now, let me make my screen bigger again. Sorry about that. I will keep forgetting to do that. But now, in this case, we've got this filter, TCP delta greater than half a second, and not TCP flags reset equal 1 or TCP fin equal 1. So exclude the fins and the resets. Show me where my TCP response time was more than half a second, and I could come in here and say add that as a filter. We could call this slow TCP. I'll hit OK. So now I've created another canned filter up there. This allows me to more quickly go through my trace files and start finding out where there's problems. Okay. So as we go through here, you notice that I added columns. So we can add anything that's shown in our decode window here, we can add that as a column. So we can start bringing some of that stuff up to the surface. Let's take a look at a fun little trace here. So I'm going to open recent. We're going to open our DNS problem trace. We'll close that. So here, I was teaching a class in Orlando, Florida, and I was out by the airport, and we were having a heck of a time connecting up to the internet. So we decided, hey, this is a network analysis class. Let's go ahead and troubleshoot this and see what's going on in here. So in this case, we did a capture of our DNS traffic. So we see that our machine right here sends this DNS query for Google to 4.2.2.2. Okay. We get a reply back in 141 milliseconds from 4.2.2.2. And it tells us that Google is at 0.0.0.1. Oh, now that is the IP address to have. That is a cool IP address, 1. Now, does it make sense that Google's at 1? Not really. So let's take a look at the next one. So 1.6 seconds later, we send another query for Google. This time we get a reply. And if we look at our answers here, 64.233.187.104. Well, that sounds plausible. That sounds like a good IP address. So here we start going in and we take a look and we get a good reply there. But now we get 1 again. So one of the things that I always look at when I start seeing things like this, I am curious who's responding. I want to know where that server is. So there's a fun little field inside our IP header that lets us know where the response is coming from. So if I take a look at my IP header in here. I go into the Internet Protocol. What we find in this case, let's click on this, is we have our time to live. Now, anytime we send an IP frame, we put in a time to live value. And every time it goes through a router hop, it decrements this value. So I can use this as a way to get an idea of how many routers I've gone through. So in this case, this machine was starting out at 128. So if I come in here and I look at the response, I see that my time to live is 62. Now, this could be as high as 255 to start with. That'd mean I went through about 193 router hops. That's a lot. Or it could be 128. That's still 62 router hops. Or it could be 64. 64, that seems short. If it's 64, that means that one of the root DNS servers is residing at the Orlando Inn and Suites at the airport. And that seems very unlikely. But we notice that our time to live is 62 right there. Now let's look at one of our good responses. That has a time to live of 245. That seems plausible. That would be about 10 router hops if it started at 255. Let's look at another good response. 248. 7 router hops. That's plausible. Here's a bad one. 62. So let's raise this up. Let's make this a column. So now, and we can take next sequence number and let's get rid of that column. We don't need that for this. So now we see that every time we get a bad response, it has a time to live of 62. So what was happening here? Well, in this case, what we were running into is at the hotel, they had a box that made us sign in to get onto the internet. This box was broken. And the way that they forced us to sign in was by intercepting our DNS traffic. So it was broken and it was responding to any DNS query with 0.0.0.1 part of the time. So we were able to narrow this down based on the number of routers that we knew we had in the classroom and go back and say, in this case, we strongly believe that there's something wrong with your system here. They said, yeah, we've been getting complaints by other people. So they got permission from corporate to reboot this box and the problem went away. So oftentimes we run into firewalls, we run into load balancers, we run into other devices that could be in the middle of the network that could be responding as if they were the device at the far end. So by going in and looking at things like the IP time to live, we can get an idea. Are we actually getting a response from the same device? That's kind of one of those little tricks in there I've learned over the years for being able to go in and take a look at that. So, this is one of the things with packet analysis. I could absolutely go on for days on some of the things that we can go in and take a look at in here. Let's take a look at another little trace. This one, outlets. So here I did a packet capture, and I'll be honest with you, one thing I usually like to do is I turn off colorization. There are times where I care about that, and there's times where I don't. Sometimes if traffic is not encrypted, we can see some interesting things in here. If I say TCP contains, I can type in a field, or I can type in text, and it will search all the frames for that text. So right here, I see break. What this is in this case, these are some Wi-Fi attached outlets I have here in the office. And I captured the traffic to and from those devices and the rest of the internet just to find out what were they doing. So this break is when we turn the outlet off. So I was able to capture this and see what ports are being used, what the IP addresses of my outlets are, and who they're communicating with in this case. And I could come in and I could use something like GeoIP lookup to find out where that device is. In fact, if we go in, let's see if I've added it in here. I may have not redone it. That's one for another class. Is we can go in and we can add in the GeoIP database within Wireshark, and it will tell us where that IP address is. But now I can use filters such as TCP contains to search for specific text, or UDP contains to search for specific text within my traffic. So I'm going to keep an eye out here for questions. If you have any questions, I want to make sure that I get those answered. But one of the things with doing packet capture analysis, and this is a very, very brief introduction into using Wireshark, but is you got to be curious. If you're not a curious person, you're going to have trouble with this. The other one is practice using this before there's a problem. Don't wait until there's a problem. Somewhere around here, I've got my fire extinguisher. It always makes my wife nervous when she comes out here and I've got the fire extinguisher sitting on the bench. But I use the fire extinguisher as an example that most fire extinguishers say pass on them. Pull the pin, aim the fire extinguisher, squeeze the handle, and sweep side to side. A protocol analyzer is not a fire extinguisher. It's not that easy. So first off, we want to get in the path of the packets. We want to make sure that we are capturing the packets that are having the problem. Then we want to move in and start capturing or start analyzing those packets. There is one more thing I want to show you. So let's go in. I'm going to share my screen. We're going to make Wireshark a little bit smaller. So back here, I've got, let me close a couple things up here. Let's see. Well, here, I'm going to close Wireshark for a sec because it's got one of my screens jammed up. All right. So earlier, I showed you go back. That switch. So if we zoom out a little bit, what I have connected to that switch is a Raspberry Pi. So sometimes we need to be able to go in and capture over a long period of time. So what I've done is I've taken this Raspberry Pi and I've configured it so that the Wi-Fi card in the Pi connects to the network. I've configured the wired port right there so it does not attempt to get an IP address. All it's doing is listening. And I've connected that via a very short Ethernet cable over here to my GS105E. So this is my sub $100 packet capture setup. So if we come in and we take a look at that Pi, what we're going to do is we're going to stop capturing for a second. And let's see if we can make that font bigger so you can see it. We're going to type in what I believe is one of the most useful commands when it comes to doing packet capture. So let me switch back over to our screen, or we've got our screen up there. Okay. So I'm going to come in and I loaded T-Shark up on this Raspberry Pi. So I did a sudo apt install T-Shark. T-Shark is the command line version of Wireshark. So now I can come in and say sudo T-Shark minus I eth0. So I'm going to capture on interface Ethernet 0. Then I'm going to say minus B. Now there is a pile of command line variables that are available for Wireshark. But this one allows me to specify how many files are going to be in my ring buffer. I'm going to say 100. Then I can say minus B file size. I'm going to say 50,000. Now this is measured in kilobytes. So this is a 50 meg file. So I use the combination of files and file size, and I base that on how big a drive I have in that device. So this has 128 gig micro SD card in it. So I could go with a lot more files if I wanted to. Then I say minus W, and we'll say webcast.pcap. So here's what this is going to do. It's going to capture on Ethernet 0, which is the port that's connected to our little inline tap. It's going to keep the last 100 files, and it's going to set that file size to 50 meg for each file, and each one is going to start with webcast. So I'm going to hit enter. So now it is capturing all the traffic going to and from my computer. Now, if we come over here to this window, and we look at the directory where I started that, what I see is here I've got these files right here. Now we see that we've got a new file called webcast. So what's going to happen is every time webcast hits 50 meg, it's going to start a new file. Now, if we look at the timestamp on this file, we have 2021, we have 11:04, we have the time and the date. Now, the time is off on this machine. Apparently, it thinks it's closer to 5:56 p.m. But in this case, it shows me when each file started, and then I can see when the next started. So this is a great way to go in and capture over a long period of time. I could take this setup, I could put it under somebody's desk. I could let it capture. And then when they have the problem, the intermittent problem, what I can do is go back and say, what time did that problem occur? And I can go grab the trace files that I captured during that time. Because this is the other big one when it comes to capturing packets. You need to be there. You need to have something capturing when the problem occurred. So here we went in and we created a little setup using a Raspberry Pi and a $35 switch to get us in line, capture the packets, and write it to disk. Now, if you really wanted to get fancy, you could load things like zero tier up on here so that you could access this from outside your network. So once I do that capture, I can stop it. I could transfer it over to my machine. Now, this takes a little bit of work, right? Because you've got to get these files off of that Raspberry Pi. We could do a SCP command in the Mac. We could copy it over. We could use little applications in Windows like WinSCP that makes it easy for capturing these. I've gone in and created just a little web page so that I could get to them. But the thing that we can't see is we can't see the live packets going across, right? Because now we're doubling our network traffic. So when we're using something like this, we're setting this up to capture for a very long period of time. Now, one little trick that I'll do is I will put an icon on the person's desktop, and that icon will send a ping to an IP address. Doesn't matter what IP address. But by doing this, it puts a marker in the trace file that I can go back and find again in the future. So if I came back here, let's do that again. Yeah, we're almost at 50 meg right there. There we go. So we hit 50 meg, we started the next trace file. Now, we could go in and use T-Shark to display this, but it's just going to run through all the packets. I would need to transfer this file. Now, the beautiful thing with this command over here is I can run this command on my machine. So on my Mac, I could come back and run it on my Mac. In Windows, you can run it on your machine. So if we want to capture this, we can take an old machine. We run this command right here. T-shark -I is the interface. -B files tells us how many files we're going to save. -B file size shows us that. All right. Well, we've been going for about an hour. So I'm going to conclude this webcast. I want to thank you for joining me. We're going to do these every week. It's going to be on some topic. We'll come back to some more advanced topics on Wireshark. If you have any questions, anything you'd like to see me cover, comment in YouTube, send me a message in LinkedIn, put something on our Facebook page. But I hope that you found something out of today to be useful. I always sit in and listen to other people talk about things like Wireshark because there's always a different approach that they may take. All right. Well, thanks for joining me, and I hope to see you in a future webcast. We'll keep sending these things out and doing them. So thank you very much, and have a great day.